In this video, we discuss learning outcome number 2 of lesson 6.3, which is all about the sampling distribution of sample proportions and its relation to the population proportion. So just as a reminder, the sampling distribution of the sample proportion p hat is the distribution of all values of that sample proportion p hat when all possible samples of the same size n are taken from the same population. Here's some notation. We use p hat, pronounced p hat as it shows on the slide, for sample proportion. And this is an estimator of the population proportion, which is just denoted by p. Now here's a graphic that we looked at in the last video. We said that if you have some population of size capital N and you randomly select with replacement n values from that population, and then you find the proportion p hat from each sample. So you select n and then you compute a p hat. And then you select n again with replacement and then you compute another p hat. And you do this for all possible samples of size lowercase n. And you've got all of these sample proportions. If you then look at the distribution of those sample proportions, it turns out that the distribution tends to approximate a normal distribution. It's symmetric about the mean. It starts low, then it's high, and then it's low again. And it's symmetric about that middle 9. And sample proportions turn out to target that population proportion. So what I mean when I say target is that when you take the mean of those sample proportions, you expect to get the population proportion. Or in other words, the mean of that distribution of population or sample proportions is equal to the population proportion. So let's look at an example. I love this example because it makes concrete all of the ideas that we just talked about. Now suppose we've got a population consisting of 3 numbers, 4, 17, and 11. In order to understand sampling distributions, better, we're going to compute a population proportion. We're going to compute some sample proportions for all the possible samples, and then we're going to see how the mean of that sampling distribution compares to the population proportion. And we'll do this through a number of steps. So in part A, we're asked to find the population proportion of even numbers. Well, there are 3 numbers on that list, 4, 17, and 11. Only one of them is even. So the proportion of even numbers is 1 out of 3, or 1/3. Then we'll want to list all possible samples of size n equals 2, selecting with replacement. And then we'll find the sample proportion for each sample. And then we'll summarize the sampling distribution in the form of a probability distribution table. This is going to be very similar to those probability distribution tables that we looked at in chapter 5 when we discussed discrete probability distributions. And then lastly, we want to show that the mean of the sample proportions, so that's our average value of the sample proportions, or the expected value of p hat, is equal to p, the population mean. So first let's answer part A. It says find the population proportion of even numbers. There's 1 even number out of 3 numbers. So the population proportion is 1/3. Notice that I'm using capital N for the size of the population. We use lowercase n for the size of the sample. Now we want to list all possible samples of the size n equals 2 when we're selecting with replacement. I can list this on the slide for you, but I think it'll make a lot more sense if I show you on my piece of paper. So I will show you my paper now. Okay, so our population consists of 3 numbers, 4, 17, and 11. And we're asked to find all possible samples of size n equals 2 from this population when we're sampling with replacement. So if I'm selecting samples of size n equals 2, the number of samples that I can get can be found using that multiplication counting rule. If I've got 3 choices for my first number, And then I put that number back in after I've chosen it. And then I've got 3 choices for my second number. And then I put that number back in. I have a total of 9 possible samples of this size because I'm selecting 2 of these and I'm selecting 2 of them with replacement. So there are 9 possible samples. Again, this is the number of ways I can choose one of these. I've got 3 options. And then this is the number of ways that I can choose the second one of those. That's because n is equal to 2. So if I want to list the samples, I can draw that tree diagram that we started drawing very early in the semester. For our first number, we could choose the 4, the 17, or the 11. And then for our next number, we can either choose 4, 17, or 11 again, or 4, 17, or 11 again. 4, 17, or 11 again. So our 9 samples are the 4 and 4. So we could choose the 4 twice. We could choose the 4 and then the 17. Choose the 4 and then the 11. We could choose the 17 and then the 4, or the 17 and then the 17, or the 17 and then the 11. Or we could choose the 11 and then the 4, the 11 and then the 17, or the 11 and then the 11. So since we have 3 options here and we've got 3 options for that second choice, there are 9 possibilities. Okay, so those are our samples. Let me go back to my PowerPoint slides now. Okay. And I just listed them like that. I listed them as ordered pairs. You'll see some possible samples are listed as ordered pairs when you're doing your homework. Now, the next part of the question asks us to find the sample proportion of even numbers for each sample. I'm going to do this on my paper as well. So I want p hat for each of these. Well, I've got 2 options, 2 different outcomes here, and 2 of those are outcomes are even. So the proportion of even numbers here is 1. So it's 2 out of 2, which is 1. Here, the proportion of even numbers is 1 out of 2. Here, it's 1 out of 2 as well. And I've got 1 out of 2 here that are even. 17 is not even, so I've got 0 out of 2 there, 0 out of 2 there. Then I've got 1 out of 2, and then 11 and 17 are both odd, so I have 0 out of 2, and then 0 out of 2. So the possible p hats that we would get are 1, 1/2, and 0. So the sample proportion will either be 0, 1, or 1/2 because the sample is going to be one of these. Let's go back to our slides. Okay, so we've got our samples, all 9 of them. And then we list the p hat for each of those. Now, in part D, we're asked to summarize that sampling distribution in the form of a probability distribution table. I will do this on my paper as well. So basically, you just want to list all of the possible p hats that you have. And we see that we've got 3 of them. So p hat could be 0. We might have, for a particular sample, 0 even numbers out of the n equals 2 numbers on our sample. Or you might have a sample proportion, of 1/2. So you might get 1 even and 1 odd. Or you might have a sample proportion of 1. Maybe they're both even. And then we want the probability associated with each of those. Well, there are 9 different outcomes, 9 different samples here, and 4 of those give us 0. So 4 out of 9 is the probability that p hat happens to be 0 for that particular sample. And then the probability that p hat, our sample proportion, is 1/2 is, well, I've got 1, 2, 3, 4 of those as well out of 9. And there's only one way out of the 9 ways that we could get a sample proportion of 1. That's if we chose the 4 twice. So that's 1 out of 9 ways. Notice that if you add all of these probabilities together, you have 9 or 4 out of 9 plus 4 out of 9 plus 1 out of 9. So that's 9 out of 9. So the probability of getting one of these is equal to 1. But the sample proportions that are possible when you choose samples of size n equals 2 are 0. You have no even numbers, 1/2. You could have 1 even number and 1 odd, or 1. You could have 2 even numbers. So let's go back to our PowerPoint slides. And now we're asked to show that the mean of the sample proportions is equal to the population mean. I don't think I'm going to do this on my paper because I think you can see it just as easily on the slides. But typically I would do this on paper. So remember how we computed the mean of a discrete random variable when we were talking about probability distributions, discrete probability distributions in chapter 5. Basically, we had a bunch of x values and we associated those with probabilities, and then we multiplied the x's by the probabilities, and then we added those together. This time, instead of having x values where x is some outcome of a random variable, the random variable that we're looking at here is p hat. That's a sample proportion. So if we want the mean of the sample proportions, all we have to do is take the sample proportions, multiply by the corresponding probability, just like we did in chapter 5, and then add those together. So we're going to have 0 times 4 over 9, which is 0, then half of 4 over 9, which is 2 over 9, and then 1 times 1 over 9, which is 1 over 9. So when we do that, we compute those, the p hats times the p's, and then we add those together, and we get 1/3. Now the question asks us to show that the mean of the sample proportions is equal to the population mean. So what we see is that the population proportion, that's the proportion of even numbers in that sample, or in that population, which was 1 out of 3, because we had 4, that's 1 even number out of 3 numbers on our list, is equal to the mean of the sample proportions. Now you might be thinking, like, that's kind of surprising because the sample proportions could only take on values of 0 and 1/2 and 1 when you have samples of size n equals 2. But they're distributed in such a way that when you compute their mean, you actually get that true population proportion back. That's going to be true for all distributions of sample proportions. Okay, so that last example was an example that's very similar to what you'll see in your homework. This example is a little bit better as far as showing you what this process can do for you, showing you what a sampling distribution of a sample proportion actually tells you. So let's say you're repeating this process. You roll a die 5 times, and then you count the number of odd numbers, or you find not just the number of odd numbers, but you find the proportion of odd numbers. So if you're rolling a die 5 times, well, before we get into that, let's look at the question. The question says, what do we know about the behavior of all sample proportions that are generated as this process continues indefinitely? So we're going to keep doing this. Again, we're going to continue rolling a die 5 times and then looking at the proportion of odd numbers that we have after rolling a die 5 times. Now, here we are looking at results from repeating this process 10,000 times. So that means 10,000 times we rolled a die 5 times, and each time we counted the number of odd numbers that we got, and then we used that count of odd numbers to find a sample proportion. And then we looked at all of those sample proportions together, and then we graphed them. So this is what we got. So let's say you roll a die 5 times, and the question is, what is the proportion of odd numbers in that sample? If you roll a die 5 times, you could get 0 odd numbers, 1 odd number, 2 odd numbers, 3 odd numbers, 4 odd numbers, or 5 odd numbers. So the sample proportions are going to tend to be like 0 out of 5. Maybe you got 0 out of 5 odd numbers. Maybe they were all even that time. Maybe you got 1 out of 5 that were odd, or 0.2 as a sample proportion. Maybe you got 2 out of 5 that were odd, so 0.4 as a sample proportion. 3 out of 5, 0.6. You might have a 4 out of 5 that happened to be odd, that's a 0.8. Or maybe all 5 were odd and your proportion was 1. So your sample proportions are going to have values of 0, 1/5, 2/5, 3/5, 4/5, and 5/5, or 1, because those are the possible sample proportions that you could get for a number of odd numbers when you roll a die 5 times. Okay, but now we're not just going to do that 5 times or 100 times. They actually did that 10,000 times. So 10,000 times, they rolled a die 5 times, and they computed sample proportions every time, and they got a bunch of values that were either 0, 1/5, 2/5, 3/5, 4/5, or 5/5, or 1. And then they looked at the distribution of those sample proportions. It's a little bit hard to see on this slide, but you notice that distribution, when you look at it, it looks normally distributed. It starts low, it ends up high, or then it goes to being a high frequency in the middle, and then it goes back to being a low frequency at the end. It's symmetric about this middle number. And it turns out that the mean that is calculated when you find the mean of all of these sample proportions, even though the sample proportions themselves were 0, 1/5, 2/5, 3/5, 4/5, and 5/5. Turns out when you take the mean of all those, you get p equals 0.5. If you're saying, what does that mean? We're going to get to that soon. Okay, so this is like a little bit like zoomed in version of the exact same graphic. So if you look at this distribution of sample proportions on the right, you see that the sample proportions were either 0, 1/5, 2/5, 3/5, 4/5, or 5/5. Now there were 10,000 trials. Rather than listing the probability associated with each of these, what they basically gave you was a frequency. And I would probably have converted to a relative frequency. The graph would look exactly the same, but with a relative frequency, that would be an estimation of the probability of each of these different outcomes. So it looks like for 0 out of 5, they had about 250 out of that 10,000 trials that gave you a 0 out of 5. And similarly, there were about 250 trials where all 5 times that the die was rolled, an odd number appeared. So the proportion of odd numbers in that case was 1. So you've got 250 here and 250 here. And then when the proportion was 1 out of 5 or 4 out of 5, so you had one die, or one time that you rolled the die out of those 5 times, you got an odd number. And then over here, 4 out of 5 times, you got an odd number. It looks like the frequency associated with that is about 1,500 for each of those. So you could take this 1,500 and divide by that 10,000 to get a relative frequency approximation of the probability of getting that 0.2 as your sample proportion. And then it looks like a little bit more than 3,000 times, maybe 3,200 times, or maybe 3,100 times. When the die was rolled 5 times, 2 out of 5 times it was odd, or 3 out of 5 times it was odd. So notice that this is very symmetrical, and we can compute relative frequencies for each of these by taking each of the frequencies and dividing by that 10,000. I think I want to show you how to do that on my paper now, just to show you that the the mean that we get when we look at data like this is going to be very close to that 0.5. Now, there's going to be some issues with it because I'm reading a graph that happens to be very small, and I'm estimating what I see on that graph. If I actually had the counts, if I had the frequencies, it would be a little bit better. But even so, we're still comparing to a sample size or a population size which is infinite, because we're imagining doing this indefinitely. So this is not exactly the same as the distribution of sample proportions that we looked at in example 1, because in example 1, we talked about all of the different samples of size n equals 2, and then we found the proportions for every single possible sample of size n equals 2. Here, we're not able to do that because the population size is like infinite. Because you could keep rolling that die 5 times as many times as you wanted forever. But we can still talk about these distributions, the sampling distribution in this way. So I'm going to have this slide up, but I'm also going to use my piece of paper to estimate some things. So it looks like from the table, sorry, I'm bringing the PowerPoint up so I can continue to look at it. It looks like from the table, the frequency associated with these different p-hats are these. So p-hat is 0, and it seems to be about 250. P-hat is 0.2, or 1 out of 5, and that looks to be about 1,500, maybe 1,600. And for 0.4 and 0.6, those appear to be about 3,100 each. And then 0.8 appears to be about 1,600, and 1, that's a proportion of 5 odds out of the 5 times you roll the die. That appears to be about 250. Okay. Are you with me? I hope you're with me. Now, if I want to make this into a relative frequency, I have to divide by that 10,000. Now, this relative frequency is going to give you an approximation of that probability of getting this outcome p-hat. And if I'm dividing by 10,000 here, that's like moving that decimal over 4 times. So we should have 0.0250, 0.16, 0.31, 0.31, 0.16, and 0.025. Now these may not add up to 1 because I was estimating this by reading the graph, but let's see, what do we get? We get this and this together are equal to 5% of the outcomes. And then we add these two together and we get 32, and then I add 31 and 31. Actually, not bad, 0.99. Okay, so those are the estimates of the probability. These are relative frequency approximations of the probability of getting each of these outcomes p-hat. And this is using 10,000 trials, doing this 10,000 times. This is what we got. Now, if I wanted to calculate the mean value of these sample proportions, I would take each of these values of the random variable, which is the sample proportion p-hat, and I would multiply by the corresponding probability. Just like we did back in chapter 5, when we looked at discrete probability distributions, this was just called X and that was called P, but it's exactly the same principle. So I've got this times this, which is going to be 0. And then this times this would be 0.2 times this would be 0.32, and then we move the decimal over once, so 0.032. And then we've got 4 times that, so that's going to be 1.24, but then we move the decimal over. And then we'll have 6 times this, so it's going to be that, and then we move the decimal over. And then 8 times that, so 80 plus 48, that's 128. And then we move the decimal over. And then we've got 1 of those. Provided I did all of my arithmetic correct, and I often make mistakes in that. If I add these together, I should get a probability that's close to 1/2. And if you're saying, why is it 1/2? We'll talk about that in just a moment. It says 0.032 plus 0.124 plus 0.186 plus 0.128 plus 0.025. Not bad. So the mean of the p-hats, given these estimated frequencies that I was reading off of the table, is equal to 0.9 or 0.495, which is about 0.5. Okay, so now let's go back to the PowerPoint. So if we take the mean of these, we get something close to 0.5. Now, it might actually be 0.5. It says P equals 0.5, but P equals 0.5 and the mean of the p-hats equaling 0.5 are two different things. But notice that the distribution is approximately normal, and that when we came up with the relative frequency approximations for each of those probabilities, we got numbers that added up to nearly 1, which is good because the sum of the probabilities should be 1. And then we were able to calculate the mean, which ended up being 0.495, which is really close to 0.5. Now, if you're saying to yourself, why is P equal to 0.5? That's on the next slide. Notice that the sample proportions are approximately normally distributed. Now, we're saying that we're going to roll this die 5 times and then count the number of odd numbers in each sample. And so we're going to get, 0 out of 5. So 0 odd numbers out of 5 numbers, or 1 out of 5, or 2 out of 5, or 3 out of 5, or 4 out of 5, or 5 out of 5. So all the outcomes are 0, 1/5, 2/5, 3/5, 4/5, and 5/5, or 1. And then we're going to average all of those together for all of the possible times that we could do that. But we could do that infinitely many times. The question is, well, what should the population proportion be? Well, the population proportion should be 1/2, because if you're talking about a single roll of a die, the possible outcomes are 1, 2, 3, 4, 5, and 6. All of those are equally likely, so the population proportion of odd numbers should be 1/2. And it turns out when you average all of the sample proportions, that's with the 0 out of 5, 1 out of 5, 2 out of 5, 3 out of 5, 4 out of 5, 5 out of 5, and you're averaging them by multiplying by the corresponding probability. That's that proportion of times that they're showing up. We're using the relative frequency approximation of probability there. You get a mean that's really close to 1/2. And that's exactly what we would expect, because the true population proportion of odd numbers is 1/2. Half of the numbers between 1 and 6 inclusive, when we're talking about those positive integers between 1 and 6, are odds. 1, 3, and 5 are odd. 3 out of 6 are odd. So 3 out of 6 is the same as 1 out of 2, or 0.5. So the sample proportions have a distribution that looks like this. Notice that the sample proportions are normally distributed. And if we compute the relative frequency approximation of the probability of each of those outcomes p hat, what we get is, well, we can find those probabilities, multiply by the corresponding p hat, and that's going to give us, or when we add those together, that's going to give us the mean of those p hats, or the mean of the distribution of the sample proportions. And it turns out that the mean of the distribution of the sample proportions gives you the same value as the population proportion, which is 1/2, because you have a 1 in 2 chance of rolling an odd number when you roll a die once. So that is it for our discussion of sample proportions. Know that the distribution, the sampling distribution of sampling proportions is approximately normal, and the mean of the distribution of sample proportions is equal to the population proportion. So that means sample proportions, p hat, are good estimators of the population proportion p. And when we say that something is a good estimator, we just mean its mean is equal to the value that we want it to be. It's equal to that value we're trying to estimate. Now, another word for a good estimator is an unbiased estimator. It's giving us what we want, and so we're calling that unbiased. We'll talk about sampling distributions more in the next video. In that video, we'll be discussing sample means rather than sample proportions.